we have seen examples, or an example of a benzoic acid which is substituted with an electron donating group, and we have also seen the effect of that electron donating group on the acidity of the benzoic acid. Let's now take an example of a benzoic acid which has an electron withdrawing group by resonance, and then we can see the effect of that electron withdrawing group by resonance on the stability of the corresponding conjugate base or benzoate, and subsequent influence on the acidity of benzoic acid itself. So let's take 4-nitro benzoic acid. So this is 4-nitro benzoic acid, a nitro group on carbon number 4, or the para position on this benzoic acid compound. Now, if we deprotonate this carboxylic acid in order to judge acidity by looking at the stability of the corresponding conjugate base, we get something like this as a result of deprotonation or loss of a proton from the carboxylic acid unit. So this is the benzoate. We can stabilize this benzoate in exactly the usual manner that we did before on carboxylic acids in general, or the stabilizing benzoates or carboxylates in this case, or benzoates by resonance. Okay, we can take one of the lone pairs on the negatively charged oxygen. We make a double bond between oxygen and carbon, and simultaneous breakage of that carbon-oxygen double bond. If we do that, then we get another resonance form, which is this one. So we get that. We can redraw now the nitro group in order to illustrate its effect. And remember, the nitro group has the nitrogen in the nitro group has a double bond with oxygen and a single bond with another oxygen. Nitrogen has a positive charge again. That's because its formal charge is plus 1. So it's an electron withdrawing group, obviously by resonance. So let's make it withdraw. In order to make it withdraw, you can do this in a stepwise manner, or you can do it in one go. So we break this carbon-carbon double bond, we make a double bond here, we break this carbon-carbon double bond, we make a double bond there, and obviously this nitrogen-oxygen double bond must be broken simultaneously in order to obey the octet rule. So if we do that, then we get something like this. Now, a positive charge, obviously, on that carbon that's next to the carboxylate. That's because that carbon has lost its electron share. Now, this withdrawal of electrons results in a positive charge on this carbon, which is adjacent to the carboxylate. Now, this results in delocalization of electrons, delocalization of the charge, which helps or supports stabilize the benzoate. So electrons here and the negative charge are actually delocalized. So there is delocalization of electrons or delocalization of the charge. The conjugate base, therefore, or the carboxylate, is stabilized. If you like, this is a stabilization factor, a stabilization effect as a result of the electron withdrawal by the electron withdrawing group by resonance, which is the nitro group. So therefore, 4-nitrobenzoate is actually more stable than benzoate itself. That's because the charge or electrons are delocalized as a result of withdrawal of electrons by the electron withdrawing group. In summary here, electron withdrawing groups by resonance and also by inductive effect delocalize the negative charge in the carboxylate, delocalize electrons, which stabilize the corresponding benzoate, and therefore benzoic acid which is substituted with an electron withdrawing group, is actually more acidic than benzoic acid itself.